We have Alex and Chris from PyMC Labs. They'll be talking about how you can scale GPs to large data sets and stuff. So thank you so much for coming here, both of you, and we're excited for your talk.
Thank you. Should I use this?
Yeah, that's right.
Should I turn this one off? There you go. Yeah, welcome everybody. Thanks for coming. So Alex and I recently had a job swap. So he used to work for PyMC Labs, and I worked in baseball, and now I work for PyMC Labs, and he works in baseball. So I had to get out when I knew he was coming. So Gaussian processes, we've got 90 minutes to do this. It's a kind of a small niche of Bayesian analysis, but it's actually a huge topic, and we're not nearly going to get to everything. But hopefully we give you a bit of a foundation to kind of discover more on your own. If you want to follow along at home, here's a repo of Alex's that until 2 minutes ago was private. It is now public, so everybody, we were wondering why nobody was telling anything. So I'm going to give my part in slides just because I think it's a little nicer way to do the didactic stuff. There is a notebook that corresponds to my stuff for you, mostly to play with afterwards. You don't necessarily have to follow along here. And then Alex is going to do an in-depth case study in a notebook, so it breaks up the material a little bit. So anyway, let's get rolling so we don't run out of time. And even though 9 minutes is a short period of time, please do ask questions, particularly if they're clarifying questions. And of course, we'll be around after the talk for more extensive discussions of GPs and other things. This is supposed to be a way of giving a little bit of introduction to a very flexible subset of Bayesian statistics, Bayesian statistical modeling. As they call Bayesian non-parametrics, so it's a really flexible way of doing nonlinear regression classification. And again, can't teach everything in an hour, but hopefully we'll hit on the high points. The reason we like tools like this is because a lot of us, we're data scientists, right? We're dealing with a lot of real-world data that is messy, and a lot of sort of default statistical approaches are not necessarily suited for that, or it makes your life a little bit harder because data looks like this in the real world, right? It's not normal, Gaussian distributed. Why are we using Gaussian processes then? We'll get to that later. Outliers everywhere, it's skewed, it's hierarchical, all this stuff, right? Those are real world data sets. But what we learn, this is kind of how I learned it, right? This is SAS. I grew up on SAS because I'm that old. And this is kind of your textbook example, right? You run a linear regression on a set of sort of reasonably well-behaved points to relate X to Y. But of course, it falls apart when you get relationships that are a little bit more complex, and kind of the linear assumptions may not necessarily hold. This is often a good starting point, but you sort of have to do a lot more work. And the reason is because of some of the statistical assumptions that are associated with linear models, right? You've got parametric distributions for the data. We're assuming that errors are normally distributed, which they often are because of the central limit theorem and things like that. And then most importantly, it assumes linear relationships among the variables. But got to give linear models some credit. They're pretty flexible. You can model nonlinear things with linear models, obviously. So a logistic regression, we just do an inverse logit transformation to model something that's a probability. We're interested in some latent probability of an event occurring, and down its at its core, it's still a linear relationship here, or even that same data set that I just showed you that we'll look at again. This is some salmon spawning data. You can do things like polynomial regression, where you do a little bit of easy feature engineering, right? You expand, you make a quadratic or cubic or higher order relationship, and you can do crazy things, but the crazy things maybe overfit So then you got to step into things like model selection to try to determine the appropriate degree of the polynomial. Okay, so it's just a lot of manual. In the age of Claude and ChatGPT, we just don't want to be doing all of that stuff, right? We want something that's a little bit more automatic. And so, not just Bayesian inference, you can do all of that stuff in a Bayesian way, right? You can do Bayesian linear regression, you can do Bayesian polynomial regression. We're going to talk here about non-parametric Bayesian inference. So we're using Bayesian methods, and that means we're making inferences and predictions that are inherently probabilistic. Everything is using a probability distribution to describe our data, our uncertainty in our parameters, our predictions, the whole bit. Again, because this is like an intermediate tutorial, I'm not going to. This is the only time I'll show you Bayes formula, probably. Actually, no, maybe there's one later on. But this is the idea for those of you who need a bit of a refresher, right? Theta are our parameters. We, again, ascribe a distribution to that doesn't really, it really is just an epistemic use of probability distributions, right? It describes our knowledge about the value of that. If we knew theta perfectly, it would just be a point, degenerate point probability of 1 on a particular value. But then that's typically more diffuse than that, and so we want to use some data to update that to a posterior. So P of theta is prior probability, not conditional on any data. Before we looked at our data, theta given y is what happens after we've seen our data. And the magic of Bayes formula is that it allows us to convert that information, basically just flips the conditioning around. We go from something we have here, our data, so this is our probability of our data conditional on a particular value of theta, or a distribution of those values. And what we really want to know is this, right? What do we know about theta given y? So for Bayesians, data is fixed, distributions parameters are random. And by random, again, we mean random in our state of knowledge about that. Okay? We won't mention the normalizing constant here, but we'll ignore it. But what we're going to do here is a particular subset of Bayesian methods, GPs, that is involved, as the name implies, using Gaussian distributions to deal with some of this messy data in kind of an automated way. And this would seem to be kind of an unlikely candidate for dealing with nonlinear, multimodal, scary data, because Gaussians aren't particularly flexible, right? They're symmetric. They have really narrow tails. They don't like outliers. Only 2 parameters, that sort of thing. So one Gaussian distribution, that's certainly the case. But we're interested in many Gaussians. So the simplest case is a bivariate, a multivariate, in this case bivariate Gaussian, right? Where it describes now a vector of elements, parameters, what have you, and then we have a covariance matrix that describes the variance of any particular value and how they correlate with other elements in that vector. And that's going to be kind of the important part here. The reason the Gaussians are so useful to us is actually due to 2 inherent and important properties. One is the marginalization property. And it has a really cool properties that where if you just want a subset of a multivariate normal, let's say this isn't just a bivariate normal, let's say that it's like a vector of mu's for x and a vector of mu's for y. Any arbitrary subset can be marginalized from that multivariate normal. So if we just want x, we don't care about y, you'd think we have to do a big integration, but it turns out all you have to do is pick out the means from the mean vector and pick out the covariance from the variance-covariance matrix, and voila, you're done. You don't have to do anything. You get this completely for free. Okay, so if we're only interested in a little subset of our data or parameters, whatever, we can just easily just pull those out. The other property that's important is called the conditioning property. And this says that the conditional distribution of a multivariate normal is also normal. Right? Sorry, I think I forgot to say that here. That not only is it easy to pull out, but it's also just another normal distribution. Same thing here. Here. Not quite as easy, right? It looks complicated and messy, but importantly, it's closed form. I don't have to do derivatives. I don't have to do integrals, anything hard like that. The only hard thing later that we'll see is inverting matrices is sometimes hard, but it's closed form, right? So we have a conditional mean and a conditional covariance. And this is important, right? Remember all this Bayesian stuff. We're conditioning something given that we've observed something else, or given that we've updated a parameter to something else. So we can always marginalize normals, and we can always condition multivariate normals. So what's a Gaussian process then? Well, we just generalize this further. So we started with univariate Gaussians, then we talked about bivariate, multivariate. We're gonna, all a Gaussian process does is it generalizes a multivariate normal to be infinitely large. So we just have an infinite number of elements in our array. And of course, as most of us here are also probably partly computer scientists, you can't deal with infinity on computers, right? You can't store infinity. And so what do we do if we have something infinite? Well, we don't use a vector, we use a function, right? So you just pass it the values you're interested in, inputs for it to get particular outputs. So what we do is we swap out a mean for a mean function, and we swap out a covariance matrix for a covariance function. So these are functions. And what we get, what a Gaussian process is actually a distribution over functions. So a Gaussian distribution is a distribution over values. Gaussian process is a distribution over functions. So every realization from a GP is an entire function. So the cool thing about them is that we're not trying to estimate the parameters of some regression in a little bit more abstract way. We are modeling the function directly. So if there's some unknown function, latent function, we're trying to get at that exactly. Okay. And there's lots of definitions of GPs, but this is a useful one. An infinite collection of random variables, any finite subset of which have a Gaussian distribution. So anytime you pull out any values from a GP, it's defined on the real lines because it's infinite. Any subset of that is going to also be normal. And we've seen how we can do that, right? We can marginalize them, we can condition them. So, we called this like non-parametric Bayes, right? But it's kind of a silly name. We're actually talking about infinitely parametric, which is sort of the opposite. What we're saying actually is that the number of parameters grows with the data, the size of the data with the size of the model. So we just we pull out the elements of that infinite Gaussian that we actually need, and that will get bigger as we have more data. Okay, so we're going to look at these key components of the GP. So I just said that first and foremost, we have now covariance functions. Yes, sir.
Sorry, just a clarifying question, I'm not sure I understand.
Yeah, no.
You mentioned the number of parameters basically expands infinitely with the number of, with the size of the data. Aren't those the parameters though? So in that there's two parameters, both of which are functions.
They're not parameters necessarily. See, there'll be other parameters, but it just makes an infinite. In principle, it's an infinite vector, and
So
we're
it's
using
like
a function to.
So it's the distribution. The distribution is populated by an infinite number of points, but there's still just one distribution.
Yeah.
Okay.
Yeah.
Cool. Thank you.
Sure. Yeah. Exactly. And maybe it'll come clear when we explain what a GP is parameterized by. Yeah, parameterized is kind of a strange word here because it's what we're doing essentially here is we have a function that generates vectors, in this case, variance covariance matrices. So a realization from a covariance function is a covariance matrix. So if you pass it a certain number of x's, inputs that you're interested in, it just turns itself into a multivariate normal, essentially, because the realization of that is going to be variance covariance matrix. The variance covariance matrix is the key to everything that happens in a GP. All the action is in the covariance functions. And kind of the art to it is choosing appropriate ones to parameterize your particular GP problem. And there's a whole, it's kind of like, in Bayes in general, right? One of the tough things about learning Bayes is that you have to learn to work with different probability distributions, knowing when to use a binomial distribution rather than a Poisson, and being aware of kind of the zoo of available tools. And so the same thing here. So there's a variety of variance covariance matrices. So one of them, kind of a canonical or default choice is an exponential quadratic, which kind of looks like a normal distribution kernel in and of itself. It's got one key parameter here, which is a length scale that controls kind of how wiggly it is. So and sometimes you see the length scale on top versus on the bottom, and it just determines, you can make them broader, you can make them wheelier, and then sometimes there's a parameter out front that's the scale that controls kind of how it grows on the y-axis. So one controls kind of how finally it describes changes on the x-axis, the other expands and contracts on the y-axis. And so these are draws from a GP prior with no data using one of these exponential quadratics. There are other choices though. So this particular one has one parameter. Again, it can sometimes have two. And just like anything else, the more parameters you add, the more flexible it becomes. So a matern is kind of similar to an exponential quadratic, but it's got an additional parameter, nu, which is set to 3/2 because it integrates out really easily. And you can see it's kind of, it's got more, but more roughness. So as the new parameter goes up, gets larger, it becomes closer to an exponential quadratic. You go down to a 1, 2, and it kind of looks like Brownian motion, very jagged. So this kind of expresses sort of a different sort of process. And then you even have things like a non-stationary kernel, so cosine kernel, and others that if you've got, so let's say seasonality that you want to describe in your particular model. And one of the really nice things about them is that covariance functions are additive. So you can take a seasonal, you can take a cosine covariance function and add it to a quadratic exponential. And one will describe the seasonality, and one might describe changes on a different scale. Where in this case, this just has two different length scales here, right? And so you can have one that describes long-term changes versus short-term if you're talking about time here. It's not always time. And you can see that it becomes, as you add more kernels, you can get more and more nuanced, more and more flexible models built here. You can multiply them together. You can think of multiplying as kind of like an AND operator, where it's going to have high probability under both, whereas additive is more of an OR operator. It just has to have high probability on one or the other. If one goes to 0, it doesn't go away. Okay, and there's a whole, if you go into PyMC, for example, and look at our GP library, we've got a whole list of available, there's even a notebook in PyMC examples that describes each of the covariance functions. That's kind of the idea. Mean functions are functions that generate mean vectors. They're much less important. You'll see that really the posterior Gaussian process generally doesn't involve the mean function at all, but it's good for constraining, it's good for adding prior information about what happens in the mean. So often it's just set to 0. And then we let the data vary away from 0. You can set it to a constant or a linear model or something like that. You can make it more detailed, but again, if you've got a lot of data or even a reasonable amount, medium amount of data, it just gets blown away. So you don't generally waste too much time thinking about it. So a simple example of it, a GP, parameterizing a GP, would be a mean function of 0 and say an exponential quadratic. This would be your my first GP model looks exactly like this. And you don't need specialized packages like PyMC and Stan to do stuff like this. You can do it by hand, right? Here's an exponential covariance function. Voila. This one's got 2 parameters. I notice I put the length scale up top. I think it's more normal than having it below. Just got to be aware of where it is. And then there's that scale parameter. So length scale and scale, or length scale and amplitude, it's sometimes called, right? And so you pass scale and length scale. And so what each of these things do, this covariance matrix, what do covariance matrices do, it tells you how related 2 variables are from one another. And these kernels, these covariance functions, typically are like essentially distance functions. So, except for things like periodic ones that aren't stationary, x values that are closer will have higher covariance. Ones that are further away will have lower covariance. So what I'm going to do to try to make this a little bit concrete is we're going to actually sample from a GP with my first GP parameterization. Yes, sir.
I noticed you changed the parameters to theta from the L you had for characteristics length scale. Is there some intention for that? Are you going to optimize those parameters?
I changed them from what?
They were previously it was an L.
Oh, I'm sorry. Yeah, my notation just sucks.
Yes.
That's all.
So okay, I thought you were trying to apply parameters.
I think I took this from the PyMC.
Okay, so it's arbitrary.
No, sorry, yeah, it's arbitrary.
Okay.
Sorry.
No problem.
Shouldn't do that. And I'm going to set this one to a length scale of 1 and a scale of 1. And so what you get prior, we're essentially going to describe functions that kind of vary around 0 and within kind of 1 or 2 units of it. Right. But again, we haven't seen any data yet. This is the prior, right? No data. And so, but we're going to now generate a realization from our GP. Right? We're going to start conditioning and sample from it. So we want to get draws from the prior. How do we do that? Well, the first sample is easy. It's unconditional. We haven't seen any points yet. So I'm just going to pick an arbitrary x value. I just chose 1. And I'm just going to choose a random normal for NumPy. And I get a value, 0.49. And what do I need? I need 2 additional functions. One is a conditional. So here's my conditional normal again. So now I'll be able to calculate for a grid of values the GP conditional on observing that one. It's not even an observation, it's a draw, right? So I've drawn one value at a particular point of x. And because of the covariance function, it'll make values close to it nearer to that value, right? So we'll expect a little shrinkage of that band because of this, right? So this is just a Python function of that. And then the other thing is a predictive distribution. Right, sorry, so this is the update, this is the normal update, this is the normal conditioning, this is the posterior predictive distribution of the Gaussian process. So they're very similar. So what this is going to give us are predicted y values and then the sigma associated with it, which will vary along the line as well. So let's see what that looks like for drawing that particular value. So remember I drew it at x equals 1 and I got 0.49. And so I went through and I predict all of those, and now I've got y-preds and sigmas, and that's just a 1 sigma, 1 standard deviation sort of band again. And you can see how it's constricted really close to that point. Okay? All right, now we need this conditioning a little bit more. We're going to update it with another point. So I'm just going to pick another point, negative 0.7. I'll draw a value from a random normal there, append it, and run it through, and now I've got another value, and then I do that same update again. Yes?
I think I must have missed something. It was clear the covariance function that you had and the mean function, but how do you go from pulling from the Gaussian process? Like you have those, you showed those 2 functions, but I didn't see how those 2 functions were.
One is the conditional, so conditional on a particular value of x, what other values are going to be. Okay. And then the other is going to be the posterior, or sorry, not the predictive distribution that results from that.
Okay.
So I'm going to update, what I'm getting here are mu's and sigmas, and then here I'm putting those in, and giving it values, and I'm running it through the covariance function, the kernel. Kernel here sometimes does another name for covariance function.
Okay.
So that's the covariance function with the length scale and the scale, and what else is in here? X and t. So see what I've got here is we're predicting new values of y given I've got a vector of 2 y's and a vector of 2 x's. And then x star is my new, the next point that I choose. So here I chose, point. Here I chose point, negative 0.7, and that's my new value. And I need a value for that. And then I update that I have a grid of x's, which is what, where did I do this? Right. So I've got x pred is a linear space between negative 1,000 points, a grid of 1,000 points, and then I run that through the predict. And then I just plot that. Okay, so the idea here is we're using this conditioning. I don't have to do them one at a time. I can take a whole vector. There's 5 new values now, add that to it, conditional on the 2 that I've already seen. This is what the whole thing looks like. And you can see it, it's like making sausage here, right? And so I could have just passed a whole grid of values at once, but I'm trying to kind of give you an intuition of how this works. And this is random, these are random draws, right? So if I do this 4 more times, you get 4 different functions. So these are all, and you can see how they're all just kind of oscillating around 0, more or less. Because again, we don't have any data. I just said the prior is it's centered on 0 and it's got, standard deviation of 1 kind of thing. Okay? So this stuff can be done by hand. Again, we haven't seen any data yet. This is just sampling from a prior, just like drawing. This is the equivalent of drawing from almost a random number generator that we've created here for a GP. You don't have to do all this by hand, you can, but we've got a lot of packages now that do this. GPy was one of the first ones from the University of Sheffield, I think it was. And then there's ones based on Torch and TensorFlow. Scikit-learn has them. They're not really fully Bayesian there, but they've got them. And then Stan and PyMC and other things. And then newer ones are based on JAX. So we're getting a proliferation of GP tools, which is really, really nice. All right, let's go back to this data. Let's add some data now. We've dealt with GP priors, now let's have some data. So salmon recruitment, so this is number of recruits, which is baby salmon as a function of the number of spawners, grabbing females, and so there's just more females, more baby salmon. But it's kind of maybe plateauing or whatever. So it's some sort of nonlinear function that we're trying. We're modeling a growth curve, right? And the first kind of GP we're going to talk about here, just again, remember what we're doing in base formula. We've got a prior, which here is a GP prior, which we've been working with already. And we have a likelihood. And so you got to choose a likelihood. And this is, log recruits could easily be normal again. And so we got to figure out what our posterior distribution is. And this is proportional to, because that normalizing constant that I didn't want to talk about causes us problems, right? Because it involves heavy integration. But if your prior is a GP and your data is Gaussian, it turns out that the posterior is another GP. So it's conjugate. In Bayes, we call this conjugate. It happens in quite a few places, like a binomial data with a beta prior deals beta posterior, things like that. And so important here is that it's closed form again. So it makes it kind of really easy to work with. The key to learning from the data, what we're learning here are these hyperparameters, right? So with exponential quadratic, it was the scale parameter, called it theta 1, I guess, the last time I used it, and then the length scale, which was theta 2. And so we're going to learn those. That's the learning that's going on. Just like we're learning regression parameters in a linear model. And so this is what it looks like on the log scale. We typically work with everything on the log scale when we're doing Bayes. So there's our GP prior. We have a Gaussian likelihood. And then this is what we call the marginal likelihood. So when you have this conjugate form, it's called the marginal likelihood GP. And it's this closed form GP. And just one thing to note here is that there are 2 important terms in this marginal likelihood. This one is kind of a model, it's kind of a data fit term, because it involves y here. And this kind of acts as a penalty term. And so we can use optimization on this to kind of choose the appropriate values for theta 1 and theta 2, or whichever hyperparameters we have, and to keep us from overfitting. So it's kind of got a built-in mechanism for optimization. Okay, so let's implement this now in PyMC. So first, a bit of PyMC code. For those of you not as familiar with PyMC, I'll kind of explain a little bit about what the API looks like. We always specify models inside of this context manager. So we kind of hijack the context manager to build models. So anything that's declared inside of the context manager that's a PyMC variable gets added to the model. So you see we're instantiating a model. You know, we're used to using these things for like network connections or something like that. It's the same idea here. We build a model, we clean it up. And so we give it a name, and then, so we're going to specify, I've changed parameter names again. Now it's row and eta. So row is going to be the length scale, and eta is going to be the scale, just keeping you on your toes. And we're going to give these half normal. Why are we choosing half normal here? We don't have to. In fact, it's probably not the best choice. But two things that have to happen is they have to be continuous, and they have to be positive. So half normal guarantees that we're positive. So it's a reasonable choice, but not always the best one. Fine for our purposes. Okay, there we go. And so here's the covariance function. So exponential quadratic here. And then we're going to specify a mean function. And I'm actually going to give it a little bit of prior information because, you know, let's say we're, you know, we have an intuition about growth, right? It should be, you know, more females, more babies. And so we're just going to give it a rise over run linear growth mean. But again, we don't. It's probably not going to matter because we've got data. And then here's our marginal GP. This is our marginal likelihood GP. So we instantiate a GP marginal. We pass it a mean function. We pass it a covariance function. If you don't pass it a mean function, it'll assume it's zero. That's kind of how prevalent zero mean functions are. We don't even have to pass them in PyMC. And then our likelihood then is a marginal likelihood. So if you're used to building other models in PyMC, hierarchical model or something, you'd have a likelihood term that would have an observed, where you'd throw the data. Here you not only have to give it the data, it's not called observed, it's called y. We also give it a grid of inputs because remember we don't want to ever work with infinite things. So we're going to give it a grid of values that are associated with it. So you're going to pass x and y, not just y. And then a noise parameter. So this is our error, essentially observation error, right? Okay. And voila. And so model fitting here, I'm just going to find map is just essentially SciPy minimize. So we're just optimizing here. We're just going to find the mode, posterior mode. So it's not fully Bayesian. You know, we're not being true Bayesians here. But we only care about that if we're interested in the uncertainty around the hyperparameters. So all we get here are fixed values. We don't get entire distributions. But it's super fast. Yes?
I was going to ask if it's super fast.
Yeah. Yeah. We'll sample later. Okay? And so the next step, now we fit this model, what does it look like? So we got to make predictions now. We're going to take a grid of values from, you know, 0 females to a few hundred, I think it was. And so the posterior predictive distribution in Bayes looks like a big complicated integral, but you actually get this for free, more or less. This is the posterior, and then this is the sample distribution of new data. So you're just multiplying the two together and integrating over theta, but you don't actually have to do any integration here. But we've got a function that does it for us. So what we're going to do now is specify conditional. So we're going to give it a range of spawners. We're going to leave out the prediction noise here. We're just going to look at the underlying line. We're not going to worry about sampling error. And then here, sample PPC is, oh wait, this is changed to, is it still sample PPC or is it? sorry, this is an outdated API. It should be sample posterior predictive. And it might probably still works and gives you a deprecation error. And then you get the fit and then the variable you want. I'm just going to draw 3 samples, so I'm just going to have 3 lines. And you see this, 3 reasonable looking lines. Notice it didn't overfit to those 3 dots there. It kind of, gets the length scale that it estimated looks pretty reasonable. And there you go. And that's just 3 draws. You draw, 1,000 of these if you wanted to estimate kind of the uncertainty around. Any questions there? First GP or first marginal GP?
None of these are using that graph estimate, right?
Yeah, they are.
They are?
Yeah, that's how you got, it takes these values, rho and eta and sigma, just those fixed values.
You just pull out those two.
Yeah. Yeah, notice the cool thing about the API is anytime you want to add something to the model, you open up the context manager. Just add
Is that just used under the hood? I didn't see those variables passed to the function.
No, but the Sentiment model has it. Sentiment model includes all the variables that are now
And they're
fit to
just
those.
accesses into the
Yeah, they're set to those values. Okay. And then if we're interested in predictive noise, we can now call it salmon pred noisy. Do the same thing, and now we get, so every line there's potential. So that includes just observation variability and other things that we're not interested in modeling, but will still potentially affect the values we see in nature. All right, so again, we live in a messy world with messy data. What if we don't have a nice closed form marginal likelihood thing? What if we have data that's not normally distributed? The example I used here is just from some data I worked with back when I was an academic at Vanderbilt. I used to do infectious disease modeling, and this is from a measles outbreak way back in 1997 in Sao Paulo. And there we had the data is essentially you just have somebody come in with a febrile illness, and you're interested in whether or not it's actually measles or not, and it may disproportionately affect different age classes and result in kind of biased assessments if you don't get kind of the disease right, and the probability of confirming as measles can vary by age. And so we're going to model this probability of confirmation. And so now we've got clearly binomial data. It's number of people that come in at that age group and how many cases there actually are. And so now we've got binomial data with the GP prior. We no longer have the conjugate output. We have we have a GP of some unknown form. Well, GP is always Gaussian, but we're going to use it. We're going to transform it to use to estimate parameters of the binomial. So this is what we call a latent GP likelihood. So before we had marginal, now we have latent. These are the 2 major classes. Looks the same at the beginning, but the key difference is now our GP is latent. Sorry, it should be, latent. Notice I didn't even give it a mean function here. And then now we have GP dot prior when we pass it at greater values. So it's a little bit different. And then we get a transform, right? So what is this GP going to represent? It's going to represent the probability of confirmation. But of course it's Gaussian, which is not a good choice for modeling probabilities, right? Because you get negative values and get values that are greater than 1. So we do a transformation. So we just do a little inverse logit transformation. And then we fire it into a binomial, standard binomial likelihood. So we're not using marginal likelihood anymore. We're using our classical PyMC, just binomial likelihood with an observed, pass the data to observed. And now we can do MCMC. We can do MCMC before. It's fine. I'm just mixing it up here. So this is kind of the de facto standard for doing Bayesian inference, which is Markov chain Monte Carlo sampling. So it will assign an appropriate sampler. In this case, it's the no U-turn sampler, nuts. Runs a couple chains. Took about 4 minutes. It's a relatively big data set.
Chris,
Yes.
could you do the MAP there if you
Yeah.
want? Okay.
Yes, you could. Again, it all depends on whether you care about the uncertainty in the hyperparameters. And so this is what it looks like. And so you can see it does a nice job of kind of identifying the fact that the variation increases with older age groups, mostly because of sample size, not because they're inherently more variable. You see probably got a lot of zeros here just because it's 0 out of 1 and 0 to 3 kind of thing. And then you get kind of distribution of plausible posterior functions there that describe the change by age of confirmation. Kind of the major issue with Gaussian processes in practice is scaling them with larger data sets. So you can see even back here, it took 4 minutes. It's not terrible, but as your data gets large, it's an infinitely large model, so parameters isn't an issue, but as the data gets large, GPs can get slow. And the reason is, it goes back to when I was talking about the conditional before. This is the posterior GP. It involves a inversion of a realization of the covariance matrix, or function, which is a covariance matrix. So it's going to be x by x. So imagine that's like 1,000 observations. And you're inverting a 1,000 matrix every time you do an iteration of MCMC. So it gets very expensive. In fact, it scales cubic with compute and quadratic with memory. And so not great. So we have strategies for dealing with that. One is what we call a sparse approximation. We can sparsify our data here. And what this involves is choosing what we call inducing points or pseudo inputs. We choose a set, essentially a subset of the training points that kind of encapsulate the variation in the data. And so this obviously reduces the expressiveness of the model because we've got less data. So it's always going to be a kind of a trade-off with performance and expressiveness. So, for example, let's take the running of the Boston Marathon in 2015. So we've got 26,000 people. So 26,000 by 26,000 data matrix, not great. Let's say we want to estimate, finishing time by age group, which is always interesting. I'm not close to qualifying for Boston, even at my age. What we do here is have a sort of a subclass of marginal GP, because marathon times will tend to be normally distributed, even though they have to be positive. But they're, I think they fall broadly under what's the term I'm thinking of? Never mind. So we use the marginal sparse approximation here. What it requires is having some inducing points. So we choose some value m varies much less than n. We're just going to use 20 inducing points. And we have a little utility in PyMC GPs that does k-means. So it's going to use generate clusters and get centers of those clusters and use those as inducing points. And we're going to use the marginal likelihood approximation. There's a few different approximation methods. FitC is the default. I'm not going to go into the details of those. That typically just try the default. If it doesn't work, I try one of the other ones until it works. They vary to the degree which they underestimate the noise variance, which is going to happen here. Some of them will actually overestimate it, so it's good to try a few of them if you're going to go this route. So we have this marginal sparse now, and then inducing points, and then we pass the inducing points as well as the original data here. And we get something like that. So this model just simply wouldn't run as a full GP. I can't remember how long this one took. Yeah, 30 minutes or so to estimate. But so we have exact inference, but it's using a approximate prior, so it's trading off something else. Yeah.
Is the k-means trick there? Is that like a common approach that will work to reduce that dimensionality, or is it just kind of getting lucky with this example?
No, it's a good way of picking, sort of intelligently picking points. Like this is a pretty dense cloud of points, and so they're more or less evenly spaced. As you get older, so you want more points where the data is denser, obviously, and so it kind of serves that purpose. But you can do, if you've got a lot of data, which you usually do, if you're doing a sparse approximation, you can sometimes just pick a grid lin space, and it'll usually work. It's really just how sparsely you want to treat things way out here. All right. Passing them both, but all of the inference is done based on the inducing points. But you're still interested in the whole, making inference on the whole thing. So that's where the conditioning comes into play. An even better approach to this is a different type of approximation called Hilbert space GPs. This is a parametric approximation that reduces the dimensionality for this cubic to mn plus n, where n is really small. M here is going to be a set of basis functions that are derived from the covariance functions. So we actually did take spectral density approximations to them. And so each of the covariance functions in PyMC for which we have decompositions will have that, and we can run HSGP on all of them. And the cutting to kind of the chase, what we're approximating our GP with now is actually almost a linear model where we have this latent parameterization where I have these basis functions. So phi here are our spectral decompositions, which are only depend on the inputs x, and then beta are a set of coefficients. Again, almost like linear model coefficients that only depend on the hyperparameters. And so it kind of pushes our task here from choosing between, well, it adds to the task, I guess, because we have to choose length scales and things, but we also have to choose how many basis vectors. And obviously, more is better, more faithful representation of the true GP. And then what we actually do is we define the boundary of the space over which we want to have a valid representation of the data. So it's sort of like a half width of your data. So we end up having to center our data and then define kind of the half width. And so as we take more L's, you sort of want it to be 1 or 2 times or more larger than the range of your data. So you choose these parameters based on your, the trade-off, primarily between 1 and 2, approximation accuracy and computational efficiency. Those two trade off in an obvious way. And then also, where in the X space do we want to make predictions? Do you want close to the end, like outliers? Do we want to project outside of the data? That will also govern our choices here. And this is kind of the implication is, let's say we have data that ranges from -5 to 5, and we choose L equals 5. You can notice they all converge to 0 at the boundary there. And maybe in some cases you want that to happen, probably you don't. So you want it to be larger. So we choose L equals 6, so just beyond the data. You can see now they're a lot more flexible, and even more so here. But again, as L gets larger, computationally it gets more intensive as well. And in the paper that kind of describes HSGPs, that you get nice little heuristics here to help you change, so as your length scale gets small, which means you're describing kind of more detailed processes, the number of basis vectors that you want also increases. That's a logarithmic scale, so that kind of gives you an idea here. And just as an example here, I'll use the Cherry Blossom's data set. If you read Herschel McElreath's book, he's got a chapter or 2 that deals with this. These are 827 years of dates recorded where cherry blossoms bloomed in Japan, and they also recorded the temperature as well. So we deal with modeling this temperature data, the temperature on the first bloom or something like that. And so here we go, cherry blossom model. Same as this all looks the same. Eta and L, and I'm sure we're going to use a return here just to mix it up. And then now our GP is HSGP. We pass it a list of them because you can do this on multiple dimensions if you want to. but it's accepting the list there. And then we're going to use C equals 2, which is 2 times the range of the data, essentially. That's what that means. And then this is a latent GP, so we use gp.prior. And essentially, we're just going to create a linear model here. I'm going to add an intercept, and then F is going to be my approximate GP. So you can just drop this in as just an arbitrary, latent, nonlinear submodel, if you like. So it's really, really handy. And then the likelihood, it's a transform GP, but not really, since we can express this on the real line. Don't have to do any transformation. We're just going to use a normal likelihood here. And then run it on sample. If you really want to accelerate things in PyMC, you can use alternative backends. So I've been using the default C backend. If you've got NumPyro installed, JAX, you can run a NumPyro backend. So if you're on a GPU, you can use GPU acceleration. Or even if I'm on a CPU, it'll generally run things a lot faster. And so we get something like this. RVs is a package for doing posterior processing for PyMC output. And see, the time series might be a little bit overfit, I don't know. So, the first step of the modeling, though, is the first model. So the caveats with HSGP, and then I'll pass it over to Alex here, is that it can only be used with these stationary covariance kernels. With the exception of periodic, there is actually a hack for making periodic ones HSGP compatible. It actually doesn't scale that well with input dimension. I only showed univariate GPs here just for kind of convenience. But if you've got more than like 3 input dimensions, so you can do like space and maybe space and time, but once you get past like 3, probably will suffer. And it may struggle with more rapidly varying processes. So in other words, it won't work for all problems, particularly if you want to have like a warped length scale or something like that. But it's a really good kind of starting place, runs much, much faster than your standard GPs. Happy to take a question while Alex gets set up. But hopefully that was a good kind of little foundation. And then Alex is going to use a sports analytics case study to kind of show you from soup to nuts how you start with a data set, build a model using HSGPs, and kind of evaluate and iterate on that model. But happy to answer any questions if you've got it in the meantime. Yes?
So it did look a little overfit. Like, how would you deal with that in your workflow?
You could adjust the priors that are associated with the length scales. So that's a length scale issue right there. It may not be overfit, right? I mean, it could. Remember, that's a year scale, so that's a compressed, kind of a compressed time scale.
Would
these
you
are
like
temperatures, so that may well be a properly fit set of temperatures.
Right. So, like, how would we know? Would this involve like coding up a manual cross validation, or like are there things that help you?
No, you would never do cross. So you probably don't want to do cross validation, but that RVs package, in addition to having post-processing and plotting capabilities, also has model diagnostics. And one of those diagnostics is something called PSLU, leave one out cross-validation, and it uses the MCMC samples to do pseudo leave one out. And they show in the paper that it's equivalent to doing leave one out without actually doing leave one out. And so you could use leave one out to do model selection on different length scales if you wanted to.
All right, other questions? No? Then big round of applause for Chris, please. Awesome. So we're gonna do so Chris did the hard thing, the theory, the groundwork, and so on. Now I just get to swoop in and show you the code. Fun part. Just some internal sweeping of the repo. There was a double line in the pixie.toml, I think you will. So I fixed that, that's pushed. So if you had trouble installing your environment, you can now do that. So I'm gonna show you that. How much time do I have?
Yes, so 45 minutes.
Okay, great. 45 minutes. So we're gonna dive into a sports analytics case study. I work in baseball, which means I cannot show you anything baseball-like. So we'll do some soccer stuff because that's also awesome. That's a case study I developed with Max Gabel, who is at Bocconi University in Italy. And so here in the pre-game ramblings, you have a bit about the theory behind the model, but I'm not gonna dive into that today, but you can look into that. Basically, the idea here is to develop a model to identify, isolate the inherent latent skill of a player, taking into account the strength of the team. And we can do any complicated stuff on that. Today we're gonna look at something quite easier, which is gonna be a binomial regression on top of which we're gonna have a latent GP, as Chris showed you just before. So that's what we're gonna do. We're gonna have also variables which take into account the strength of the team's opponent and the team of the player, which are called factors in this kind of model that comes from the financial literature, which is factor models. So here you have some data preparation, stuff like that. You remember Chris told you we're living in a messy world with messy data. Well, here we really are working with messy data because he's in the data set. So here I'm taking just a subset of the players just for efficiency of sampling, but you have the full data set on the repo. That's going to take a bit more time to sample, but that's actually sampling quite fast. If I remember correctly, on my Mac, which is M2, it was taking like 10 minutes, something like that, with a lot of players, so that's good. Here's the data. I organized it by player, season number, and the kickoff of the game. And here, that's the variable we're really interested in. That's the one we're trying to infer the number, whether the player is going to score. We're only looking at forwards, so center forwards and wingers. And so here, by game, we know whether the player scored 0 or not, 1. And the season number kind of encodes the experience of the player at the highest level. Right? So here, Mr. Eggleton, that would be his first season, so he's just starting out. And then as he ages, we're gonna increase that number every year, every season. You can see, for instance, an English legend, Wayne Rooney. Here we have up until 15 seasons here in the data set. I do here just some standardization of the factors, so the team effects. Okay, so nothing very new here. I only have 2 factors here, which actually takes into account already quite the variance, because you're just looking at the difference in points of the 2 teams, right? So 2 opposing teams. Actually, if you know the difference in points before the game, it gives you already quite an indication of the strength of each team. And then I also take the goal balance. So if you have, since we're interested in the number of goals scored, if you know you have a very high scoring team facing a team that's crappy at defense, for instance, that gives you an idea. That's going to be way easier for the strikers. Here you have the histogram of the data. So you can see empirically the scoring rate is about 1 in 3 in our subset. So 1 in 3 times a goal is going to be scored. I think that's quite good, right? How is it in hockey? It's higher, I guess.
Yeah, if you're good. I mean, it depends how good you are.
If you're good, yeah. Sure. The players here, I did on purpose. I have a blend of NAB players and a blend and other like top players. You saw one NYC. I think I put Ronaldo in here, and even Cristiano Ronaldo. So both. So here, that's the important part, the HSGP parameters. We're going to use HSGP. Probably you could use inducing points too, but HSGP is really cool because it's really, really flexible. It's very versatile. It works on a lot of use cases. Not more than 3 dimensions, as Chris said, but it's really, really flexible and versatile, and it feeds really fast. So you have, though, to choose 2 hyperparameters that are going to be fixed, that you're not learning from the data. That's M and C. I put the link to 2 tutorials in the notebook. Here, beginner one, and here a more advanced one where we walk you through 4 use cases, and in the first one we really show you how to choose M and C. But in a nutshell, if you increase M, which is the number of basis vector, it's going to help the HSGP approximate GPs with smaller length scales, but that's going to increase the computational cost. That's the main thing that increases the cost. C doesn't increase the computational cost. That's really only M. If you increase C, that's going to help approximate larger GPs, larger length scales, but that means maybe you're going to have to increase M to compensate because you're going to lose some power of the approximation for the smaller length scales. Something very important when you're choosing M and C, you have to take into account the out-of-sample prediction range of your data. If you're interested in predictions, you have to take that into account because otherwise you can end up in the case Chris showed you. Remember these 3 plots? There was the one to the left where the vectors were pinching at 0. You're gonna get that, and so if you do that then and you predict outside of that range, the approximation is not valid and your predictions are gonna be correct. So you have to take that into account. And often, something very important is when you increase C, you remember that's gonna extend basically the basis vectors. That means the first one sometimes ends up being completely flat, and you were also able to see that in Chris's plot really to the right. The first one was flat, which is a problem if you have an intercept in the model because then you have 2 intercepts basically. So I'll show you how to deal with that in the code. Here, what we're gonna do is we're gonna have 3 GPs. That's the cool thing of GPs. You can like mix and match them up as you want. And so here we're gonna have 3 of them. One long-term one, which you can, is gonna be across season, and you can think about it like an aging curve. Like how do players age? And you can a priori have in mind that it's going to be like a parabolic curve, right? You could even use polynomials for that, but actually it's not really completely parabolic, but you don't really know what the functional form is, so that's why here GP is really appropriate because you don't really know, you want to let the data guide you here. Then we're going to have a medium-term GP, which is going to be across game days, and this one you can think of as capturing the form of a player. I don't know if you say the form or the shape of a player in English actually, because the form is like the, anyways, that's my French, you know, like, but the shape of the player or the form within the season, right? So maybe they start strong and then they like dip a bit because they get tired at the end of the season because the number of games increases and so on. And then you have the short-term GP. You can think of that kind of as a garbage can, right? Where it's like everything that's not picked up by the 2 previous GPs, which actually makes sense from a domain knowledge perspective. That 3rd GP will just pick it up, kind of like an observational noise GP. We could actually have another covariance which would actually be white noise, but we don't do that here. So that means we have 3 GPs. So that means we have to choose, but the 3 GPs have 2 different axes, like seasons and game days. So we have to choose 4 sets of M and C, 2 M's, 2 C's. Let's start with the game day GP. Here is what the match day, game day distribution looks like in the data. So if you follow soccer, you're not going to be surprised by that. It goes from 1 to 38. So there are 38 games in a soccer season. So that means our short-term and medium-term GPs will get inputs in this range, okay? And here actually, it's not gonna get bigger, right? They don't add usually features every year, so it's gonna be like, the X is gonna be fixed. How do I choose the length scale though? Because I have to choose a length scale as Chris said, and then I can choose M and C, and I'll show you why. The length scale, the cool thing is that it's really related to domain knowledge. So when we choose it, You can talk to a domain expert, or if you're also an expert of your domain, you can really think about it. Here, the way I do it is like, I'm like, okay, a reasonable length scale for the short-term GPs is between 2 to 5 game days. I just want something in that range. And then the medium term, I want something that's like almost a half season, even maybe more. So 15 to 25 game days sounds like something I want. So what I do here is I use a really cool package called Pretties that does maximum entropy on the optimization of that function here. That's an inverse gamma distribution. So that's like a gamma distribution to have the parameters being positive, because the length scale needs to be positive. But the inverse gamma has a factor tail. So, and that's good when you use GPs, especially for the length scales, because if you bias the GP to have length scale closer to 0, that means you're biasing the GP to actually be GP-like, right? So you can get more like wigglier than it needs. Whereas if you have factor tails, then the GP can really go to a big length scale if it can learn that from the data. Then you're gonna get basically in the limit a linear behavior, just one line. So here, the cool thing in Pretties is you can just say, okay, I want an inverse gamma that's mainly between 2 and 5. And then it gives you the optimized inverse gamma with the parameters here. So that gamma would be like 18.1 for alpha and 59 for beta, which is cool because that saves you a lot of time and back and forth. I do the same thing for the medium-term GP, so between 15 and 25. Cool, I have that, I save that, and you'll see in a minute that Pretties works really well with PyMC, so we're going to be able to just use these objects here directly in the PyMC model. But now, what I can do is that I can use this information from the length scale to choose M and C. And we have a helper function in PyMC to help you do that, which is called approx HSTP hyperparams. You have to give it the range of the data. So here again, the full range, right, including the auto sample. So here I want it from 0 to maximum 0 to 38. I want a length scale range, so that's why I did that just before it. And I know my length scale has to be between 5 and 25. And the covariance function here, we're going to use a matrix 5-2. That's usually a really great go-to for covariance. And then it spits out some parameters here. Basically, we need at least 54 basis vectors and a scaling factors of 5.4. Now I do that for the long-term GP. It's the same process, so I'll let you read that in the notebook. You can see the season distribution. There's player bias here because, well, players age and the ones who are cut off the earliest are the worst ones. So only the best ones get to have a high number of seasons. And here, of course, these theoretically you could observe new seasons, but you're never going to observe 40 seasons, for instance. It's like, I think like with 20 seasons, you basically have what you're going to have for all players. Here we do the same thing. The length scale here, I'm choosing between 2 and 6 seasons. That was harder for me to come up with because I don't know, I've never worked in a soccer club yet, so I actually asked someone who works in a soccer club. He was like, yeah, 2 to 6 seasons for a player, that sounds quite right. So that's the inverse gamma here. Boom, we get M and C. These ones are smaller, so that's cool, that's going to be faster. And now we can implement the PyMC model. Before that, though, any questions on what I just talked about? Cool. Oh yeah, if you have questions, you have one, great. So after that, you can come and pick up some stickers. I put some stickers here. With questions, can get all the stickers. Yeah, what's your question?
What did you ask the domain expert, and why did they choose to
So yeah, he told me, well, basically between 2 and 6 seasons where you have enough information about the player. Like any season that's like, I don't know, if you give me the season of Messi 7 years ago, it doesn't inform me that much about Messi's next season. the idea is that, like, so, and between truancies, like that helps you not being too close to the previous season, so maybe you're fitting noise, but that also don't make your memory too long. I mean, this is fun.
Yeah.
One thing I'm hung up on with these HSGPs is like why a lot of the hyperparameters are sort of being burdened by the user now. And it looks like you do have some ways to kind of bootstrap like M and C, but why can't you just throw like optimization on that as well?
Yeah, that's a good question. I'm sure people are doing research on that.
Okay, so it's just incrementally they're getting better at it.
Yeah, exactly. Because I mean, HSGP is quite new. Also, I think it's got like what 2 years, something like that.
The paper was 2022.
Yeah, so the paper is from 2 years ago. Count at least 1 year for us to read the paper. Me, it takes me 2 years to understand the paper.
Get published.
You know, then we have to add it to PyMC and so on. So it's like, yeah, there is a lag, but I'm pretty sure the guys are doing like optimization on that. And once they have figured that out, we'll add that to PyMC. Yeah. Because I'm like you, I'm like, yeah, that'd be great to have that optimized. But there's already too many things to optimize and choose. Okay, but great questions, guys. You get a sticker. Okay, so PyMC model. We have to define some variables here that we'll use throughout the model building process. Here we have our player index. That's just an index variable telling us which player is which in the data set. Here we have the game days. So what I'm going to do is instead of conditioning the GPs on the full x's, I'm going to condition the GP on the unique x, because that's, otherwise I would condition the GP on like 0 to 38, and then 0 to 38, and then 0 to 38, that's stupid. So I'm just doing that once, and then I index the GP, because it's always going to be the same thing, okay? So what I'm doing here is that I create the unique game days, and then I create an index of the game days that we're going to use to index the GP. Same thing here for the seasons, but I already had the season index in the dataset, so I don't create it. And then we create something that's called coordinates. That's a way in PyMC to specify shapes, but by name instead of numbers. So that's cool because if you're changing, like if, I don't know, if the number of players, for instance, change, you don't have to change the shape, you just change that array here, players ordered, and that's going to be updated automatically in PyMC. Also because it's way easier when you have multidimensional data to think in terms of counties, regions, states, players, etc. than like 50, 39, etc. Like you get lost in translation. And then I have this timescale coordinate, which is our timescale for the GPs, short, medium, long. And now we're going to define the model. So I could do that in like a whole block code, which is probably what you would do in a production model, right? You have your Python file with a huge context manager and boom, hold the model in one block. But here, for pedagogical purposes, it's actually great to open the model context, and then we'll define step by step the model. What I'm doing here is something that's called data containers in PyMC. That's to make the model aware of the data it's using. And that way we're going to get that afterwards in the inference data object that we get back from fitting, which is great for plotting and also reproducibility, because you can just give that to someone and they can just reproduce your analysis. So here we're defining the factor data, the game day ID, player ID, season ID, and our observations here. You can see I'm using the dimensions here, which are the keys from the coordinates I have here. Okay. And so, for instance, the factor data is like dimension observation ID and factor. Here we have two factors. And now, the interesting part, the player skills part of the model. Here I need another player. Why? Because I'm doing kind of I'm doing partial pooling, so that's a hierarchical parameter. So here I'm defining the player effect, and you can see my dimensions is player, so one parameter per player, and I'm initializing the prior, the mean of the prior, to the mean, the empirical mean, on the logit scale, because remember we're using binomial regression, so we're going to have an inverse logic link down later. But what I'm doing is I'm also using sigma here, which is a parameter that you'll see in the literature often called shrinkage parameter. I often call it diversity parameter because it's a bit more instinctive, because the bigger it is, the more diversity in your group. The more diversity in your group, the less pooling you're going to have. Like, because you can see that. Imagine sigma here is really small, 0.1. That means there is not a lot of diversity in the skills of the players. And so that means each player estimate is going to be pulled towards the global mean that's here. Okay? That's really useful when you have like uneven sample size. When you have a lot of data for some players, not a lot of data, very small data for some other players, and it makes sense for these players to be pulled toward the global mean, because that's going to be your best bet for the projection. But here, if sigma is much bigger, imagine sigma is 100, well then here our normal will be much bigger. So each time a new player is pulled, is drawn from that distribution, we're going to get something much bigger. So here we have that, and I use pretties again to set the prior on the sigma here for the players. And so you can see pretties works really well with that, because I just take the distribution object and I call the 2PyMC method, give it a name, and boom. Like I already had the distribution object, so that's really cool. And here you can see I asked pretties for a really wide prior. Mostly it's like I want the prior, which is an exponential distribution between 0.1 and 2 most of the time. Under the hood, pretties has a default of putting 94% of the mass in the distribution. Here it's really hard for the exponential distribution, and so that's why pretties is telling us here the requested mass was 0.94, but the computed one is 0.8. That means pretties could only put 0.8% of the mass in this interval, because the exponential has a really fat tail. But that's fine. I don't really care for it. That's a prior, and that's fine. Then now we're defining the HSGPs. That's the really fun part. We'll start. I think I'll start. Yeah, let's start from below. So here is the GP for within seasons. So remember, this one has two covariance kernels. We'll see how we combine those in a few minutes. But here, Chris showed you already, we have that GP within object that we create here with the HSGP. We pass the M that we selected, the C, the covariance that we're going to define. And you see here, I drop the first basis vector. Okay? So that's really easy. Just drop first equals true, that's done, boom. And then you have your prior GP, you condition it now on the gain base. And that's where the GP is going to be computed. That's the multivariate not under the hood. And here we just pass some themes. And that's it. That's it. Like that's the whole thing to define the GP for the within seasons.
I don't think I described why I would drop the first basis vector, did you?
Yeah, I did.
You did.
Yeah. So that's when, just for a reminder, since we have intercepts in this model, we have the player effect that we just defined. We drop the first basis vector because it's going to be very similar to the intercept. And so if we don't, very probably we're going to have an identifiability. So here is where I define the covariance of that GP. And you can see it's just the sum of the short covariance and the medium covariance. And that these covariances are the amplitude, the eta parameters that Chris was using. So I usually don't use Greek letters because I don't like that. I never remember what the parameter name is. I just use like very explicit names. Amplitude, and the other one is a length scale. That's very long to write, so I just say ls. And so these we can use some cool stuff in PyMC, which is like vectorized definition. You can see here I'm indexing amplitude 0, 1, ls 0, 1, and this is defined here. The amplitude is the so I'll get back to that in a minute because that's a bit special. But the length scale is here just the distributions we specified with pre's, remember? We put the alphas, the betas, and here we have the dimensions of the inverse gamma, which is the time scale. So it's going to define a 3D vector, okay? And then we can just index it as I'm doing here. So now, the prior and the amplitude, it's actually a cool trick. I use that almost all the time. This is called a penalized complexity prior. So use the prior and the amplitude. If you have a good prior for the amplitude, that's cool, you can use that, but sometimes you don't really have a great idea. The PC prior is really something cool to just specify something like here, where I say, well, I think there is a 1% chance that the amplitude is above 0.75%. And why 0.75%? Because we're modeling scoring rate. So I don't think that from one season to another, the amplitude is going to go from like 0 to more than 75% scoring rate. Like that'd be a huge variation. So I'm saying there is a 1% chance above that. Since we're on the logic scale, sigmoid of 1.1 is what I want. And so here I define the alpha scale, upper scale. There is a paper about that. I'm just implementing basically what they say in the paper. And then here you define an exponential prior with these parameters, hyperparameters that you just defined here, and you have a prior. So that works really well. So that's all good. And then we have to define the other prior, the other GP, sorry. Here I'm defining it another way just to demo it. There is two ways to define GPs, HSGPs in PyMC. There is the simplest one we've seen here. But sometimes you're going to want to do some fancy stuff, for instance, having several GPs, but which are using the same covariance. So instead of defining GPs all the time, since they are going to have the same basis vectors, you use the same basis vectors, but then you define another GP. And that's how you do it. So here, that doesn't change. That's the same. But here, that's changing. I'm going a bit lower level in the API here. And here, we're using a method that's called prior linearized. And that's where you condition the GP on the seasons. And then you have to be, it's a bit more verbose, but it's much more versatile. So here I define the basis coefs with the normal likelihood. And this is a non-centered parameterization, so we just want a standard normal. And here we can define the GP on the long length here. Okay, I know I'm going very fast here, so if you're interested in that, in the advanced HSGP tutorial I'll link to, we really go through that step by step. Okay. But that's a really cool trick here. That's very useful. Now I just add up all of that in the alpha, which is what we're after. That's the player's skill. So we have the player effect, and then we have just variation of the player effect on that. So that's the two GPs, F within. And you see I index it for game days here, and then the long GP that I index for season here. Here I have the slope for each of the factors. I'm gonna go faster here because that's way easier, and I only had like 7 minutes left. So, but here we have the likelihood now. We have our regression here, which is the sigmoid or the inverse logit of the alpha plus the dot product of the vector data with the slopes, and that's our P. That's our probability of scoring. And we plug that into the Bernoulli likelihood. You remember it, we had like zeros and ones, so that's a Bernoulli distribution. We just put that here, and boom, that's all good. Here we have the model graph, so it's a good model. It's like almost 7K observations, so it's not trivial, but there is much more in the data set. We have 27 players, 38 game days. We had 53 basis coefs for the within season. 31 for the long GP, so you can see how everything relates together. That's really useful, especially for debugging. We do prior predictive sampling. Don't think I have a lot of time to go into that, but I really encourage you to look into that because the idea here is that that's going to give you an idea of how to set up the priors, and that really helped me because at the beginning my priors were like horns, So I had like priors really high probability on zeros, really high on ones, and that was stupid. So I made it so that the prior scoring rate here is between 0.1 and 0.8, which is very wide prior, but much smarter for the model. And that's the prior predicted goals scored. So that's what the model is expecting before being fed to the data. And you see that makes sense from what we know about football, right? We don't expect more goals than no goals. And here I do a prior simulation of the GPs. So that's very useful too. Here we have our two GPs within season and across season, which is kind of the aging curve. And here you have the total GP. That's a priori. Okay. Then we sample. That goes fast. 2 minutes. We're using here what I'm using NumPy here. Here I'm doing some stuff to check the effective sample size, stuff like that. So if you have questions about that, feel free to ask. But here, basically, the diagnostics are good. This is also the effective sample size. Here, everything looks good here, basically in the sampling. So we can go and check the posterior parameters. I'm gonna go very fast here, but here you can compare the prior and the posterior for each of the effects, right? So here you can see the model learns that basically playing at home, that's the first line, home pitch, is a really big advantage. The balance, the goal balance difference is a really big advantage too. The points diff, the model is more like, once I know about the goal balance and the home pitch, there is not really a lot of value in knowing the points difference between the teams. Here, these are the standard deviations, the player effects. So here that's cool. Our model passes the stiff test, which is often called the Messi test. You can see Lionel Messi is among the best ones, Cristiano Ronaldo, so that's really good. Neymar also, but not that much. Ronaldo also, Thierry Henry, the French guy is among the best. That's cool. The length scales, the model doesn't learn them at all. You can see that the data is not informatic at all. So that's why it's very important to have good priors on length scale, because length scale is very hard to learn in general. Here I'll show you the GPs, but I have the posterior GP that's going to be much better. Here that's the update of the scoring rate. Blue you have the prior, orange you have the posterior. Here posterior predictive checks all looks good. This is by player. Okay, these are the posterior GPs. So the plot we saw before, that's the one that's updated with the data. Okay, so it's quite noisy because it's a subset. And also you can see the aging curve is a bit weird. If you fit on the full data, it's going to look better. It's going to look like that. Okay, so parabolish, but not very much size. So players, they progress very fast, then they have a plateau, and then they get down in performance, but slower than they got up. Here though, you can see we have an uptick here before it goes down again, which is a bit weird. Anybody has an idea why? Selection of
talent. The best players.
Yeah, exactly. Yeah, survivor bias. So yeah, that's the Messi and Ronaldo effect. Like they are the oldest ones, and so the model thinks, oh, actually, when you get older, you get better. No, it's just like these players. They are like, we don't have a lot of samples. But then you can combine the GPs, and so you have like for a player across the whole season, across the whole career of a player. Now you can have an idea of how the performance is gonna change, and you have the recent season here variation. Okay, so that's really cool. We can do all that combination of GPs to get some cool effects here. And this is Lionel Messi per season expected goal, the variation of his probability of scoring. So you can see that is good, basically. And I think I'm on time. I have 2 minutes left, right? Yeah. Amazing. So that's all. Any questions? Yes.
So you had some divergences in the sampling. Do you care about them or?
You saw that. You saw that. Yeah, no, 2 divergences. That's fine. I mean, yeah, usually that's fine. If you have like more than 10 divergences, more or less, you'll care. 2 divergences, you'll be fine. Yeah.
Why not do approximate posterior things like SPI instead of forward posterior? Yes.
So you mean ADVI, stuff like that?
Yeah,
Yeah, I mean, we could do that here, right? Here you don't have to, though. So I usually prefer to do MCMC because it gives me the full distribution, and I'm sure that I'm not leaving some gains on the table. So ADVI, so Chris has more experience on that than myself, but from what I understand is that you have more assumptions, and these assumptions in the distributions can fall down pretty fast. So that means your parameters are going to be also underestimating the variance, right? The posterior variance of the parameter is going to be tends to be underestimated. So if that's important for decision making, that's better to use systems. I think you had a question.
Yeah, notice that if you run a sampler cell more than once, it doesn't work at the same time.
Yes.
It's like when you're stating
Yeah, that's because here you're executing the model cell by cell.
Mm-hmm.
So you have to recreate the model context each time you send run that cell. Yeah.
So you have to just tell it clear out the last one.
No, you have to create the context model again. So that's why usually you do it in one cell, but here to show you really compartmentalized, I did that. Are we good? Other questions?
Maybe it's a longer question. The validation, like how do you, like maybe like visualizing that the data's, that the model's really fitting the data well?
Mm-hmm.
Just wondering. Like,
Yeah. I mean, yeah. So a bunch of stuff. So that thing, for instance, you have a bunch of like technical validations. So that's what I'm showing you here. That's posterior predictive checks. So per player, you can see the fit is really good.
okay.
It's like the blue is the posterior, the orange is the data. So you can see the fit is really,
Yeah.
the fit is really good. You can also use stuff like, R square. You can compute any test statistic you're used to because you have posterior samples. So then you can just compute any test statistic you're used to, you want to. You can do leave 100% validation also if you have several models. As Chris said, that's the technical side. Here, I mean, you can also do like domain knowledge validation. Here, what I do often on the baseball side is when I have a model, I have a call with my boss who knows baseball perfectly, and he'll be like, okay, show me that player who is like an outlier for the stuff we're studying, and that way we can see where the model, breaks down. So that's also very valuable, and that's almost a non-technical validation, but a very, very interesting one. Yeah. Thank you.